So welcome to the Science Place. We're going to do a little electric theater performance for you. But first I have to give you a few warnings because there are some dangerous things in this for particular circumstances. For instance, if anybody has a heart pacemaker, you probably should not stay inside this room. It operates much in the same way as microwaves where it can interfere with the normal functioning of a pacemaker. So please, if you have a pacemaker, leave the auditorium for safety's sake. Second of all, if any of you have hearing aids, you may pick up hordes of static time to time due to the machinery we are using. However, anytime the room gets dark, all you have to do is manually turn down your volume and you'll be okay. Then turn it back up as soon as the room lightens up again. Also, if you have cameras with you because you like to record history wherever you go, and you want to take pictures of this show too, which is fine by me, please turn your strobe off when you're not taking pictures, because our machinery is capable by remote control of turning your cameras on and getting photographs of the bottom of your chin. Now we're going to get ready to begin our show. Up in the booth we have Tracy operating light failures and slide functionings, and on stage with me we have Beverly operating the big machines. A hand for the support staff. My name is Paul and we're going to give you an electric theater show starting right now. Let's go. Children I hear. Yes, it does set them off occasionally, I'm sorry to say. Thus, we give you a warning before the show starts. And for everybody else sitting in the front row, stay in your seats at all times. Do not be inclined to leap up on stage, right? Good, okay. We begin the electric in the sky, the storm, and they didn't know who was in charge. They didn't know why it came down. They knew to do one thing, and it was this. We still do, because it's good advice, even today. But 250 years ago, an American inventor lived. He helped solve the first mystery of what lightning was. Who do you think about when you fly a kite in a thunderstorm?
Ben Franklin.
Ben Franklin, thank you, participatory audience. That helps. Benjamin Franklin, you, the audience, you know you don't look quite right for the part yet. Something is missing. I think I can fix it. Move your hands. There we go. What do you think? Is there a resemblance? Yes, there is. You've lost a little weight, though. Take a look. That's what you used to look like. You will look like that later, about 40 years, I'm afraid to say. Now, you're going to be our Ben Franklin today, okay? Okay. You're going to show all of them your most famous electrical experiment. But first, we have to begin at the beginning. We have to begin with, what did scientists know at the time you were alive, Ben? That was 200 years ago. Well, electricity. Yes, I can. I know electricity is not a fluid in a jar, called a Blanket jar, which treats electricity as though it were a fluid, and it really works. It has a metal outside and a metal inside, and in between, you have to put plastic or glass to hold them apart. Now, the Leyden jar looks like this. It is a capacitor, and it stores electrical charges. And in your time, Ben, you had one of these because you worked with the state-of-the-art. Now, you stay right here on the safe side of the stage. I wouldn't stand on the middle part. Why don't you move up a little bit? That's good. You stay here on the safe side to witness. It was a stormy day when you took your son outside. Did you bring him with you? Your son. I'll be your little boy for a while, okay? And you made your son do all the hard work. You made him put the kite up in the storm because fathers have a want to do this to their sons. And he gave you the string to hold. Tough work, isn't it, Ben? Now, is it true that you really flew that in a storm? No. What happens to people that fly kites in storms where lightning can strike them? They get electrocuted, they do not get written down in the history books. Ben, you live to be an old man, you had long white hair, you had 15 children. How's that for something to look forward to? Ben didn't get killed that day because he did this experiment in a smart way. He never flew it where lightning was. He flew his kite in front of a storm where there was no lightning at all. Like that. The electrical charge that he suspected was in the air traveled down to his kite, traveled down the string to that key he had tied upon it. Now, at this point, Ben, Do you have an inclination to walk over there and touch that thing to find out what's on it? No, good answer. Ben didn't either. This is why Ben had a Leyden jar, because with it you can walk over and do this. See what we got? That's right, you can't see anything, it's invisible. How do you know if you caught anything? Well, one choice we have is to touch it. Now, I'm not inclined to do that either. Why don't we use the versorium? It's a primitive electric instrument, the kind that Ben would have had around in his day. And if I have a charge, it should move the versorium around without touching. We do have an electric charge in here. But you know what we can do that Ben could not do? We have certain devices like lights that Ben did not have, and we can show all of them this way. I'm holding the light up to the key. I asked you, do we have an electrical charge coming down to this key? We sure do, participatory audience, thank you. Ben, experiment. No one got killed. Not in your experiment. There were a few scientists that tried to copy you, and guess what happened? Yeah, they didn't make it in the history books, that's true. Now, I want you guys to give him a hand for being such a great Ben Franklin. Thank you for joining us on stage. An artificial thunderstorm. Why? Because they won't let me bring the real one inside. This is a Van de Graaff generator. Probably when you went to school, they used to be this big. Age of steroids. They grow like mushrooms at night. Now, our Van de Graaff generator job is to create electrical charges down in the bottom here, and to move that charge up to that ball on the top. Now, it's going to move the charge through this white column in the middle. The white column contains a rubber band. That moves the charge from the bottom to the top. Now, does anybody want to have a rubber band war with me? I would win. We're going to let you guys see what the charge looks like on the top when you don't have a kite nearby. Now, Beverly, let's give them a little blast so they can use their ears and hear the charge build up. The crackling sound you hear is the electric charge building up. Now, I'm going to go in and try and convince one of these charges to jump. There we go. Now, look at the range of the jump. The mathematical formula for static electricity is, for every inch it jumps, it takes 20,000 volts. You can figure out, if you want to, how much that is. Okay, Beverly, let's turn that off. I want to take all the electricity off the ball because Beverly is about to walk over here and touch it with her bare hands. And best if nothing is on it when she does so. Now that you've met our Van de Graaff generator, we can play a little game. We can duplicate an old experiment that was done 300 years ago. Scientists at that time had electric generators, and now they weren't this fancy, but they did have them to make charges. And this is one of the games they would play. 300 years ago, if you were a party host, your job was to entertain your guests. Yes, it was. You couldn't take them out to go play putt-putt. You had to do something with your own hands to entertain them. And if you had an electric generator, which some of them did, this is a game they would play. First of all, they would get a child, like some of you. And then they would tie the child up with a silk rope around his waist. Then they would hang the child from the ceiling of a room. So the child is dangling in midair, sort of like Superman. And then they would use an electric generator and electrify the child's body. Does this sound like entertainment? It was the 17th century. What do you want? And this is the 20th century. There are laws for the humane treatment of dogs and children in this century. We can't tie them up. But we can stage instead. For this, we need a child. A child with a heart of boldness. There's some stairs over here, so you don't have to climb up. You have a dress. You look very nice. We'll keep you proper. Get in. Marissa? Nice name, Marissa. Did you bring your mom with you today? No. Okay. Stand on up there, Marissa, right on that plastic stool. This is the same as being tied from the ceiling and hanging in the air, because you're not touching the ground, are you? Okay. Now, we're going to charge up the Van de Graaff generator way up there. And I want that electric charge to move down to your body. Now, the best way to move electric charges is through conductors. Metals are really good, because they let electricity go through nicely. Aluminum up there, copper through the wire there, down to this aluminum ball right here. The charge will arrive at this ball, and you're going to have your hand right there, on top of the ball, because she's a conductor too. And once the charge arrives at your body, it's going to stay there, because I have you standing on an insulator. It's plastic, and the charge will not leave you once it gets to your body. Now, all you have to do, Marissa, is to keep this hand right here. Don't move it. Now, leave your other hand there, and you just stand very still, because you're going to feel weird. It makes your skin feel real weird. But it won't hurt you. Just keep that hand right there until I tell you to let go. I have to get all the electricity back off you before you let go, okay? You understand that? Okay. Now, we're going to electrify you, Marissa. Keep your hand right there. Don't move. Just relax. Let's try it, Bev. Oh, hang on to that dress. Don't let it go anywhere. Now, shake your head. Shake it heavy. Hard. Okay, stop shaking. That's enough. Imagine hanging sideways in a room, and this happens to your child. Now let's turn her off. Now all your hair doesn't go down. It's all doing this. You still are full of electricity, Marissa. I have to get it off your body with a lightning rod before you can let go. Otherwise, those little bolts might go looking for you. Now you just stand still. The lightning rod will suck off the electricity just like a Geiger counter. Hear a little crackling sound. There, now you're safe to move your hand again. Yeah, just like this. Yeah, you're safe and you're okay. You did very well. A hand for Marissa. Come on. There you go. You did great. Marissa helped us to look at a simple little rule that electricity must follow, plus to show us the truth that adults have found ways to frictionate it with a little bit of wool. When you have a positive and a negative charge around each other, they do this. They are attracted to each other. But we didn't do that to Marissa. Some people do this. You wonder how they get those hairstyles? That's how. Now, lightning and the Van de Graaff generators are examples of static electricity. You're probably fairly familiar with them in a more common sort of way. You know, winter comes along, you scuffle your feet across the rug, you walk up to your little brother or sister and you go, you never do that, do you?
I do.
Oh, they always are quick to say, I do! These are static electrical. I think we ought to pause a moment and give it a small round of applause. It's an important year for electricity this year. And with batteries, people could start to do all kinds of experiments they could never do before. This is one, done by a man named André Ampère in France. An iron bar, which personally, by itself, I think is uninteresting. Look. It doesn't do anything. Now, Ampère, and try it out and see what happens.
I can do it with my ear.
No, I wouldn't hold it at the time. I don't think so. We're going to try a wire, okay? It's a little more common as a conductor than telephones. Beverly gives me 2 wires to play with at this point. One is very fat, one is very skinny. We're going to do a little experiment and send a little bit of electricity through a wire. No. Bev, let's send a lot of electricity through a wire, okay? Yeah, okay. If we're going to send a lot of electricity through a wire, which wire would you pick? The red one? Or the black one? Let me see some hands. Vote. Red. Thank you. Black. Thank you. Everybody who didn't vote, you have to stay to the next show. This is participatory. Bev put a copper wire between these poles, and next time we might try a telephone there. Now, that's a small wire. She's going to send a current through that wire. It's going to have 900 volts. Now, voltage is the pressure that pushes the current through this wire. 900 volts is a lot of push. You know those little batteries you have that have 9 volts? That's not very much push. It pushes it real slow. You can put that up to your tongue and it doesn't hurt, does it? Kind of tingles a little bit. Don't do that with a car battery. Now, the other thing the current has is amps, amperage. Now her current's going to have 2,000 amps. What happens when you send 2,000 amps through a wire that size?
Oh, I'm ready.
Let's do it. Whoa! Bev, you outdid yourself. You broke it, Bev. You think we should try this with a telephone? Hey, who voted for the black fat wire anyway? You were right! The black wire would have worked better. It would not have blown up. Who voted for the skinny little red wire? It's okay. It's okay. Even when you guess wrong, doesn't mean you can't learn something from an experiment. If you watch this experiment fail like that, if you have some imagination, like Thomas Edison did, you might look at that and say, glowing wires in the dark? What could you do with a glowing wire in the dark? And you know what? You might get an idea. He did his experiment 10 on the back of my table. You're going to be the control operator, which means you're responsible for this box and those buttons, okay? We're going to make a transformer, and it's got to have 2 coils of wire. That's 1 coil, and we'll use this for the second coil. It's an aluminum ring. 1 big fat wire as far as the transformer is concerned. Now before we do this, I have a question for you. Can I make this aluminum stick to a magnet? No, I can't. Aluminum is non-magnetic. It won't stick to a magnet. Did you know that? You know what, though? Even though it's not magnetic, we're going to persuade this aluminum ring to think it's magnetic. Okay? We can do this by making it into a transformer. You're the control operator. When I tell you to, you're going to put a current through the first coil. It's going to make a magnetic field pointing up. And then a current's going to go through your second coil, making another magnetic field pointing up. And then the current's going to alternate. It's going to go the other way in the wire. And when it does, the bottom magnetic field goes upside down for just a second, and 2 north poles hit each other. You know when you get 2 magnets and you try to push the north poles together, you know what happens? Yeah, push the red button and show it to them. They repel just like that. Wasn't that fun? Let's do it again. Oh no, don't let it hit you on the head. Whoa! We never know quite where it's going to go. Give him a hand. He did really well. He did good. Now out there in the museum, there is an exhibit that you push the button on. It has a list thousands of times, back and forth, every single second. And when you do that to a current, it's not going to stay inside the wire anymore. It's going to snap free and fly through the air. Wireless electricity. We call this stuff radio waves today. You heard of those, right? Listen to radios, right? Now this little transformer right here can make them for us. It's a Tesla coil. And it works like this. Beverly's got a transformer right here, which is going to make the voltage go up from 100 to 15,000. That's a lot more. Then it's going to put that current into a capacitor, just like that Leyden jar Ben Franklin was holding. And then it's going to throw all the current into this first coil, made of some really fat wires that will not melt on the stage. And then the current goes into the second coil, which you notice is not small, but tall. The bigger it is, the more windings of wire around it, the higher the voltage is going to get when it gets to the top. The frequency will get very, very fast, thousands of times a second by the time it hits the top. As a matter of fact, Beverly is going to show you what it looks like. Let's show him, Bev. Now, would any sane human being... I'll show you what he did. You, sitting right there, yeah. Yeah, come on down here. Okay. And you, yeah. Oh, no, not me, please. Stand right here on the floor. On the floor, okay. Let's get you up here, too, right next to him. And I want... Who's in the rear? I can't even see that far. You in the yellow shirt. Yes. Come and stand down here next to these two guys. And you hold the skinny one, and you hold the other skinny one. You're holding Mr. Tesla's light bulbs. Now your job is to stretch your hands up as far as you can in the air, like this. Stretch out. That's good. That's good. Beverly, let's send them some radio waves. Hold them up as high as you can. Okay, Bev. No wires, Mom. Not a wire in the house. Did you feel anything on your bodies? Nothing at all. You came to the science place and we turned you into a human lamp. Let's give each of them a hand for bravery again. You might recognize some of these light bulbs that Mr. Tesla made. This is a fluorescent tube. At the beginning of the show, it is a Tesla coil, it is a transformer, and you can call it anything you want to, as long as you start with the word Mr. Now, a transformer is going to have two coils of wire. The first coil is back here. 125 volts goes into it. And this is the second coil. You notice it's rather large this time. Remember, the bigger it is, the more windings of wire around it, the more voltage the current receives. Now this one's going to get rather excited. As a matter of fact, it's going to be in the neighborhood of 2 to 3 million volts by the time it hits the end. Show it to him, Bev. Ooh, I think we remember that. Now, a Faraday cage. I like when the words come up behind this. A Faraday cage. We can play with our Tesla coil with a Faraday cage. It was created by Michael Faraday, the same guy that brought you alternating current by moving magnets in and out of coils of wire. Now, Mr. Faraday had a fertile imagination, and he asked himself the question, what would happen if I built a room out of a conductor? Now, this Faraday cage is surrounded by a conductor, a metal screen, the same kind that you could use if you're in the mood to go build a rabbit hutch. I think it looks like a giant bug zapper. And it has some interesting capabilities. Bev! Would you come up forward, please? Would you step inside here for a moment and inspect the interior? Mr. Faraday asked what would happen if you built a small Faraday cage and you hit it with a little bit of electricity. At our disposal, we have millions of volts. Now, this Faraday cage is big enough to contain a living human being with no living relatives. And it is parked roughly 5 feet away from a Tesla coil. That's not very far at all, is it? How you feeling, Bev? What I want to know is, will she survive this experiment? What do you think? Let's vote. Yes or no? Who votes yes? Please? There's a few of them there, Bev. I'll tell you what, everybody. Why don't you say goodbye to Bev? And I want to assure everyone that I am perfectly safe back here. Too late, Bev. Here comes a 2 million volt bolt. Get ready. Whoa, I think I got it pretty good. Let's check out Beverly and see if we have to get a new assistant for the 4 o'clock show. Bev. Ow! You're not the same, Bev. You're not the same. Have you ever seen The Fly?
Yes.
She's okay. Lucky for Bev, Faraday cages do their job. When electricity hits a Faraday cage, it's a conductor. And the electricity must stay on the outside. Anything inside the conductor is safe. Thus, Bev walks away sillily. Now over my head is a large... We looked at static electricity, which people have fooled around with for hundreds of years. Lightning, Van de Graaff generators. Then we looked at electrical current, the kind you can send through a wire when you want to do a little bit of work. But my favorite is the radio wave. The wireless electricity you can send through the air. It can carry voices, music, or live power to turn light bulbs on. Every day, all of us use electricity one way or another. And yet we don't really think about what we're doing. We just turn things on. But imagine what would happen if all your battery things and if all your plug-in things were just suddenly gone. Your world would look like this. At the beginning of the show, we said lightning used to be a mystery until Benjamin Franklin showed that it was just another form of electricity. And with special transformers like a Tesla coil, we can create lightning on stage for your entertainment. And just for fun, to end the show, we like to catch it in our hands. Try that at home. Thanks for coming to the Electric Theater. We hope you enjoy your day in the science place. Have a good time today.